Dear friends and dear colleagues, we continue the lectorium on algebraic graph theory supported by the Mathematical Center in Akademgorodok. And today we are resuming the mini course devoted to geometrical topics in the theory of self-similar fractals. And the second lecture in this course is titled Weak Separation Property and Self-Similar Jordan Arcs. And it is my pleasure to introduce the lecturer of this course, Professor Andrei Tetenov from Sobolev Institute of Mathematics and Novosibirsk State University. So please, you're welcome.
Okay, thank you for coming to our course. And I begin the second lecture devoted to weak separation property and self-similar Jordan arcs. So, the first thing which we can see in self-similar sets, that these self-similar sets are non-homogeneous. For example, if we take a Sierpinski triangle, you see it, and slightly shift it, then the measure of intersection of the shifted triangle and the initial triangle will be less than half of the measure of initial triangle, no matter how small is the shift. So now we shifted Sierpinski triangle to 1 divided by Hello, Mary. Hello, Mary. Hello. I sent you the link by Telegram. Yes, it's the same link as I used, but it is a different kind of session. Okay, because now so if we take a Sierpinski triangle and slightly shift it, and then consider the measure of intersection of initial triangle and shifted one, then we'll get that this intersection has measure which will be less than the half of the measure of initial triangle. And if we take Sierpinski carpet, which you know very well, no matter how we shift, then the intersection of shifted Sierpinski triangle with the initial triangle will differ from the measure of initial carpet to about 1/4 of its measure. So the more serious change happens with counter set. So if you take the counter set and slightly shift it, I will show it to you on the picture. For example, this one. If we take, do you see the picture? Hello?
Yes, we see.
It's okay, okay. Consider the counter set. So I draw it as just an interval with a 1/3 gap. So it will be 0, 1/3, 2/3, 2/3, and 1. If we translate it to 1 divided by 3 to the power of n, and take the counter set shifted by this distance and intersect it with the initial counter set, then the intersection will be countable, and the measure of this intersection will be 0 in the measure in the dimension of this counter set. So dimension is a logarithm with respect to 3. And if we take counter set and shift it by 2/3 and intersect it with k, then this intersection will have the measure equal to 1/3 of the measure of k. Oh, 1/2, sorry, 1/2. Because each of the copies has 1/2. So no matter how we shift the self-similar set, if this self-similar set is not some domain in plane or space, and if it has holes inside it, then whenever we shift it slightly, we'll have this measure drop in the intersections. Sorry, 1 second. I cannot see my PDF. Oh, it is here. The other problem of non-homogeneity of self-similar set can be shown on this picture. You see, if we take von Koch curve and shift it to 1 or 2/3, yes, 2/3, then the intersection will be 1/4 of this von Koch curve. Yes, this intersection will be a very small part. You see, this intersection is shown in black color. And if we change this shift, no matter how we change the shift, we cannot make this set, the shifted set, we cannot make the shifted set to coincide sufficiently with the initial set. Yes. From the other side, if we take a self-similar curve and try to shift it in such direction that, in such way, I need to shift to the other. Oh, this way. If you take a curve, if you have a smooth curve, then it is possible to slightly shift it in such a way that the image of this smooth curve will not intersect the initial curve. But this is impossible for contour. This is impossible for von Koch curve, because it's not possible to shift it slightly or even to expand it slightly, so that the image of this set will not intersect the initial set if this expansion is close to identity. There was a very interesting work which was published in 2011 by Andreas Tamas Keleti and Andreas Matte. They considered Sierpinski sponges. And when they considered Sierpinski sponges, they showed that no matter how small is the shift of Sierpinski sponge, the measure of intersection jumps down when we slightly shift the sponge. So it turns out that if a curve can be shifted slightly along itself, if a curve can be shifted slightly along itself, then it may be smooth. Why? Because if we take this curve and slightly shift, then we can repeat this shift arbitrarily many times, and after repeating this shift, we'll get a epsilon net on this curve, which will be placed on some smooth line. And passing to a limit of when epsilon tends to 0, we'll find that the limit curve must be smooth. So either self-similar set admits small shift and it is some object which has a non-zero interior in some dimension, or it is a smooth curve, or it cannot admit arbitrary smooth changes under which the intersection of changed set and the initial set will be sufficiently large. So we studied, so I and some of my colleagues studied these questions for many, many years. So first, it was the paper of me and Vladislav Aseev on self-similar Jordan arcs admitting structure parameterization. So we proved that if a Jordan arc is the attractor of a system of contracting similarities in RD, and if it possesses a structural parameterization, what does it mean? I will explain what it means. Structural parameterization. So suppose we have some self-similar curve. Since a curve is self-similar, or since this is a self-similar curve, it can be parameterized by unit interval. Yes, but if this parameterization corresponds also agrees with the self-similar structure of the set. For example, this set consists of 4 copies, and then here we have 4 copies on the interval, and such that copies on the interval, the pieces of self-similar structure on the interval will correspond to the copies in the self-similar structure of the curve. So this will be a structural parameterization of a self-similar curve. So we considered a self-similar curve in RD. So, and we showed that if it possesses a structural parameterization, and for this parameterized structure, we have an associated family, then there are 3 possibilities. First, if this associated family doesn't satisfy a weak separation property, so identity will be the limit of some neighborhood maps. So if identity is the limit of some neighborhood map, sequence of neighborhood maps. In this case, gamma is a straight line segment. If identity is not a limit for neighborhood maps, yes, then this gamma is the attractor of a Jordan zipper. And finally, there was a third possibility when some pieces of this curve have an exact overlap. So the system has weak separation property, but does not have open set condition. The next step in this search was the paper on self-similar Jordan arcs on a plane. What was proved in this paper? So, if a self-similar Jordan arc on a plane does not satisfy, you see that previous paper considered the arcs in RD, in d-dimensional space, not in plane, but in space of arbitrary dimension. But now we considered the arcs on a plane. So if a self-similar Jordan arc on a plane does not satisfy weak separation property, then it is a straight line segment. Therefore, if a self-similar arc on a plane is not a segment, then there are two possibilities. It satisfies all open set condition, and this is a self-similar zipper, or it has weak separation property, but some pieces, some copies of this arc have an exact overlap. I can tell you what is the main idea of this paper. So we considered so the case when the arc can be shifted along itself was ruled out by previous paper. But we considered the case when there is a sequence of arcs, images of arc, which approach this arc without an intersection. But you see, we already have seen that if we have a von Koch curve, then the images of shifted von Koch curve always intersect this curve. And if we have a sequence of images of some arc which approach this initial arc without any intersections, then we'll get that there will be some kind of transversal vector field, a field of directions, such that in this direction, the lines will intersect this arc only once. Therefore, it will be a graph of some self-affine function. And then it is easy to show that if we have a self-affine function with smooth graph, then this graph is a straight line. So this was the second paper. Now consider the third. The third one, was a self-similar Jordan arcs in the graph-directed system of similarities. So if there is a self-similar Jordan arc in RD, and this arc is not a straight line segment, then it can be represented as the attractor of some self-similar multizipper. or graph-directed system which has one-point intersection property. And if gamma has weak separation property, then the multizipper has graph over C. Let me remind you what is zipper and what is multizipper. Most of us know it very well, but it's good to remind it. What is a zipper? By zipper, we mean, suppose we have a sequence of points, and there is a point which is point has number 0, then Z1, then Z2, and finally we have the point Zm. And if we have a system Sk of similarities, such that Sk of Z0, Zm is equal to Zk minus 1, Zk. So the system of maps such that each map takes first and last copy points of this sequence and sends them to neighboring vertices of neighboring points in this sequence. So what does it happen with our points? So we can consider it in the following way. Suppose we have some polygonal line. And we can consider the several maps which replace each segment of this polygonal line by the image of this polygonal line in the following way. So then we get a system which is called the zipper, and iterating this procedure, we'll get some kind of a self-similar line, yes? So zipper will be called Jordan, is the attractor of this zipper, is a Jordan arc, so we did not get to self-intersection, because sometimes we can get such zippers that this intersection occur. For example, to get the Sierpinski triangle, it happened in 1914. Sierpinski considered the zipper of such way, such form. He took this polygonal line, yes, and put arrows on this polygonal line in this order, as I have shown, and then we place the images of this polygonal line so that first and second points of this line will coincide with neighboring points. Therefore, for number one we'll get this line, for number 2 we'll get this line, for number 3 we'll get this line, and repeating these steps, we'll get that finally these 2 points will coincide on the limit point, on the limit curve. And this intersection will repeat at any scale. Therefore, Sierpinski called this curve a curve which has ramification points everywhere, right? Because it has, you see, on this interval, these 2 points will be glued together, right? And this happens on each of the intervals. So it has infinite set of double points, which is dense in this on the interval. Yes. So this construction is called a zipper. But now we can make a graph-directed version of this construction. So suppose we have one polygonal line and we have some other polygonal line, yes? And we change the order in which we repeat the intervals of one line by the images of the other line. For example, this way. Yes, and repeating this procedure will get two polygonal lines, which will be the union of images of first and second line in this order. And this construction is a multizipper. So these multizippers appear, as you know, in self-similar dendrites when we get the parts of their main trees. So now I have reminded you what is the multizipper, and we'll proceed to this frame again. So if gamma has weak separation property, then the multizipper has graph OSC. So we can consider the open set condition for graph-directed system. It is not a problem, yes? Because instead of having one open set for usual self-similar set, we can consider n open sets whose images also get inside these sets and do not intersect. So it was proved in 2006. But the problem is that in three-dimensional space, the self-similar arc, which is an attractor of a Z, even an attractor of a zipper, can violate the open set condition. So also I considered this case with some of my students, and I can remind you what I mean. We can consider such a line and this will be a zipper, and it will be a zipper in R3. And we arrange these angles in such a way that images of this curve will almost touch each other when we put them here, yes? Put them on this approaching line. So we can get such parameters for this zipper when these two copies will approach each other, and the neighborhood map between these two copies can be arbitrarily close to identity. And I'll consider and explain this example in my next lecture. So open set condition and weak separation property were considered for self-similar sets because their initial prescribed role for them was to guarantee the positiveness of the Hausdorff measure. And it guaranteed that measure of a self-similar set is positive, finite, and the dimension coincides with the similarity dimension of this set. But if we consider self-affine sets, it happens that for self-affine sets also something can be applied. Of course, if you have two affine maps, so if we have two affine maps, or two affine, some self-affine set, and we have two pieces, then will be, for example, S1 of K and S2 of K. These affine maps are invertible. Therefore, we can consider as the maps Si minus 1 as J. And we say that a system of affine contracting maps satisfies weak separation property if the family of these neighborhood maps for all multi-indices does not accumulate to identity. So we can consider the open set and weak separation property for self-affine sets and its violation too. There is one problem, that if we have this weak separation property, it has no, we cannot apply it for the dimension and measure questions, but it can be applied to geometric structure of self-affine sets. So it was, I dreamed to touch this question, to touch this problem for several years, and finally in 2020, there was a paper in Doklady Mathematics when it was proved that if a self-affine arc in the plane admits affine shifts which are arbitrarily close to the identity, then the arc is a segment of a parabola. And after that, in the next paper in 2023, it was proved that if a self-affine arc in R2 does not satisfy the weak separation condition, then it is a segment of parabola or a straight line. But if an arc is not a segment of a parabola or a line, then it is a component of the attractor of some Jordan multizipper with the same set of generators. So I'm say few words about self-similar curves in history. So it was studied in many works, just from the very beginning of the first origins of fractal geometry. The first examples of fractal curves were the graph of Weierstrass curve function, the Koch curve, and then Sierpinski triangle. And then in 1938, Paul Levy investigated self-similar curves which were zippers with equal parts. And also George de Rham described the class of two-part self-affine curves. It was in 1958. So the idea of associated family of similarities for a system of similarities was initially proposed by Christoph Bahn to analyze measure and dimension properties of the attractor. So he considered the associated map or associated family, which is generated, which consists of the maps of the sets, of the composition of maps of this way: Si1 Im minus 1 multiplied plus Sj1 Jn. These are the neighborhood maps, and these neighborhood maps are the maps which send the piece Ki to the piece Kj, but on the enlarged picture, when Ki becomes the initial K, so Kj is also enlarged to the scale of initial attractor. So if these neighborhood maps Fi, if these neighborhood maps converge to identity, it means that we'll have arbitrarily close pieces which almost coincide. And it can lead to a lot of topological and measure theoretical consequences. So we say that system S satisfies weak separation condition or has weak separation property. So if identity is another isolated point in the associated set of similarities, and we can consider more wide case when we have a system of affine maps and consider the neighborhood maps of this type, and also say that system satisfy weak separation condition if identity is an isolated point in this associated set. So what happens is if WSP is violated? So as it was proved in this paper, it leads to the measure drop. So if weak separation property is violated, then the measure of this set becomes zero in the similarity dimension. Yes. And there are different rigidity properties. First, for example, it was proved that suppose we have a system of contraction similarity whose attractor is 0, 1. So suppose we have a self-similar structure on the unit interval. Oh, yes. So if phi is the structure preserving map of the attractors of systems S and T, I already explained this in the beginning. And the identity is a limit point for the associated family, then gamma is a straight line segment and pi is a linear map. Pi is a linear map. And later, it was proved that if we have a affine fractal function defined for a system S on a segment AB, and if this system does not satisfy a weak separation property, then graph will be a parabolic arc. So we consider, so it was the first step when we considered the affine fractal functions. So it is the attractors of affines, these affine sets. So now we consider what happens if we have a self-affine Jordan arc. And first we prove the following thing. Consider a Jordan arc. And we called it locally self-affine is for any proper subarc, gamma prime and gamma, there exists a non-degenerate affine map such that S of gamma lies in gamma. Do you understand what it means? I will explain it once more. So suppose we have a self-affine arc. We don't know nothing about it. Oh, we have just some arc, Jordan arc gamma. No, not necessary, Jordan arc. And suppose it has a property. If I take a point and its neighborhood, then in this neighborhood we can find an image of this arc. Nothing more. Then we call a Jordan arc locally self-affine. So no matter where we are, no matter what kind of subarc we take, the whole arc will be mapped to some subarc of this chosen subarc. So, for example, we can consider some infinite system like of affine contraction maps such that the images of these contraction maps taken together and coming to the closure will give us the arc, yes? So we can consider infinitely generated self-affine arc, yes? Do you understand, Mahlio, what I say?
Yes.
Yes, okay. Okay. If we have infinitely generated self-affine arc, for example, an attractor of some infinite system of affine map, and it will be a locally self-affine arc. So if you have a locally self-affine Jordan arc, then we can prove something about its properties. If we have two arcs, gamma 1 and gamma 2, we say that these two arcs have a proper intersection if one arc is shifted along the first arc so that the one of the endpoints of second arc lies in the first arc, and the other and one of the endpoints of first arc lies on the second arc. So on this picture, we have two arcs, we have a proper intersection. And a affine map, G of X, is called an affine shift of Jordan arc if gamma and G of gamma have proper intersection. but we also insist that the matrix A minus identity has norm less than 1/2, and G of X has no fixed point in gamma. You see? Why? What is the reason for this restriction that G of X has no fixed point in gamma? I will show you a very nice example. Very nice example. Consider this line. So this point is 0, 0. This point is -1, 0. And this point is 0, 1. And this line is gamma. And I can take the map very close to identity, which sends xy to x divided by 1 plus epsilon and y multiplied by 1 plus epsilon. Do you see what happens with this curve? If we apply this map is very close to identity, right? Right? But it has a fixed point. Which is the fixed point of this map? Do you know? Please. Is there anybody who can find a fixed point of this map? What is the fixed point? Do you hear me? Do you understand what kind of map? So I take f of xy will be x divided by 1 plus epsilon and y multiplied by 1 plus epsilon. Can you find the fixed point of this map? Hello? Does anybody hear me?
Yes, yes.
0.
What is the fixed point?
0, 0.
0, 0,
Right.
of course. So what happens with this curve? This part will be slightly expanded and this part will be slightly contracted, but this point is fixed. And these two, the images of this curve and this curve have proper intersection. Yes, because one endpoint is here and the other endpoint is there. Yes, but we need to rule out this case because it is not the case which we need. Then must not be any kind of a fixed points on this for this quasi-translation. So this affine shift cannot have any kind of fixed points. So the main result is, suppose we have a self-affine Jordan arc in R2, which is not a segment of parabola, then gamma is a component of the attractor of some self-affine Jordan multizipper. So here is the picture of some kind of a Jordan multizipper, you see? Because A consists of S1 of A and S12 of B, right? No. Sorry, S1 of A, right? Oh, and this picture is wrong. This is one of B and this is 1, 2 of B. There are two images of B. You see? And here is this one images of B and the other is images of A. Yes. So there are 3 maps and there are 2 maps. Yes. So this is a self-similar Jordan multizipper. It's yes. So it is constructed in some maybe in IFS style. So there is no fraud. Yes, everything is okay. So a Jordan arc gamma is a component of the attractor of self-affine multizipper if we can partition this arc into sub-arcs, yes? And then all these sub-arcs will be obtained of these parts by some kind of affine contraction maps. You see? On this picture, we have the arc gamma, and it is divided into 3 subarcs, and each of these 3 subarcs is mapped to the pieces of these 3 subarcs, right? So it's a typical situation with a self-affine multizipper. So the main theorem is the following. If you have a locally self-affine Jordan arc, such that there exists a sequence of affine shifts of gamma converging to identity, and gamma is an attractor of a system of contracting affine maps such that self-similar one of the following, you see. So let gamma be a locally self-affine Jordan arc. You remember the definition, yes? And we require that one of these conditions is satisfied. First condition, there is a sequence of local affine shifts of gamma converging to identity, or gamma is the attractor of contracting affine maps such that self-similar structure gamma S does not satisfy WFSP. Really, from the condition 2 implies condition 1. But we prove it for both cases. Then gamma is a segment of parabola or a straight line. How we get to this knowledge of this arc? Oh yes, will be one more theorem, and after that we'll remember. Suppose we have 2 isomorphic self-affine structure on a segment of a parabola. And these structures do not satisfy Wick's separation condition. And suppose there is a homeomorphism which sends one self-affine structure to the other self-affine structure. Yes? If A0 is preserved by this homeomorphism, then these 2 self-affine structures coincide. If you have 2 isomorphic self-affine structures on a segment of parabola, and these structures do not satisfy Wick's separation condition, this means that they are identical. Or if they are not identical, that it's just, we have just an exchange of endpoints. Do you have some doubts concerning this? If you have some doubts, I will tell you what happens. So we have some segment. Really, it may be a line, but it may be also some parabolic segments. And we have a family of affine self-maps of this parabola. For example, this one, and this one, yes? These self-maps generate a self-affine structure on this parabola. So gamma is union of SI of gamma, right? And we know that Si minus 1k Sj k converges to identity. Then, and suppose we have the other structures. Gamma is union of Ti of gamma and Ti ik minus 1 Tj j, or let me have other numbers, In minus 1 Jm. Converges to identity, yes? So we have two structures on this parabolic segment, two self-affine structures. Then, if these structures are isomorphic, so there is a map which sends gamma to itself, A0 to the A0, A1 to A1, and which sends each map SI to the map Ti. In this case, these two structures should be identical. I will tell you more simple example. So we have a segment of parabola, yes? And we divide it in two overlapping pieces. Yes, we have got this. So we have two self-affine maps. First sends this segment to this one, and this sends this to this one, yes? And if we have some other division of this segment into two parts, then there is no continuous map which sends S1 not gamma to ST1 of gamma and S2 of gamma to T2 of gamma. Yes, the only continuous maps which conjugates these two pieces is the identity. It's fantastic. It's fantastic. But it happens if the weak separation property is violated. If the weak separation property is not violated, for example, if we take unit interval and divide it into two parts, 1/3 and 2/3, yes? And we have two similarities. First sends the interval to this part, second sends this interval to this part. Then we have this interval and separate to some part A and 1 minus A, yes? Then we can make a map which sends this vertex to this and contracts this interval to this one and expand this interval to this one. And then this map can be extended to the isomorphism of these two self-similar sets. What happens? Here, we have not violation of weak separation property. And here, we have a violation. So this is a very serious difference. So it is easy to prove this theorem. And now first I begin consider this first theorem. So suppose that locally self-affine arc admits some affine shift. Then if we can shift it slightly, then what can we do? Suppose we have an affine shift then which sends this arc, this say black arc, to some red arc. I will show you this on the picture once more. Suppose we have a self-affine arc. Yes. And there is a map which sends this self-affine arc along itself, so that the image of this self-affine arc will partially coincide with this. So this map is called a shift of this, affine shift. But if we repeat this map, then we'll get a map which sends this point. So you see, this point was sent here. And this point is the end point of this arc. Therefore, it can be sent here. Yes? So if we have some self-affine arc which admits a affine shift, then repeating this shift will get a net on this arc, which finally will jump off this arc. Yes? Therefore, if a self-affine arc admits arbitrarily small affine shift, then we'll get a sequence of epsilon nets on this shift, which will converge to some kind of a curve. Yes. So we take this shift and consider their orbits. And all these orbits will converge to the same set. But if we have a affine map, then each affine map can be, if you have an affine map, 1 second, suppose we have some kind of an affine map. For example, if you have some kind of an affine map, I'll say this, yes. Let me introduction, yes. Then for this affine map, we can find it root. If we have A, then we have square root of A, yes? B is a square root, there is a B. For any A, there is such B, that B squared is equal to A, yes? And there is some B that B to the power of M equals to A, yes? Of course, this square root can be chosen different ways, but there is a simplest one. And therefore, we can represent A as the power as a power of some B. And this representation is given by differential equations. Is given by differential equations. 1 second. So if we have an affine shift, this affine shift can be represented in the form akx plus bk. Then for each such shift, we can find unique non-homogeneous linear system. And this linear system is defined the following way. The bk will be a matrix logarithm of ak, and beta k is uniquely defined for ak and bk, such that the following equation is fulfilled. Therefore, for each self-affine map can be embedded to a one-parameter continuous family of affine maps. Yes. So each affine map can be embedded in one-parameter continuous affine group this way. And this one-parameter family defines the trajectory. For example, if you have a rotation, right? Then for each point, the trajectory with respect to this rotation is a circle, yes? And if you have a expansion, then with a fixed point, then trajectory for each this expansion will be a line. And if you have for example, affine map, which, for example, if it contracts x in 2 by 2 and y by 4, then the trajectory for this map will be a parabola. So for each affine shift, we can get a smooth trajectory of this affine shift. And now there is a picture of these trajectories, which you can, and this picture you can find in any textbook of geometric theory of differential equations. Yes, John? Hello, German, do you hear me? Therefore, what happens if we have an arbitrary close small affine shift? This arbitrary close small affine shifts will converge. Their trajectories will converge to some trajectory, and this trajectory will coincide with gamma. Therefore, gamma will be one of these curves. If gamma admits arbitrarily small affine shifts, then it is one of the curves defined by this differential equation, and then it is infinitely differential curve. But for us, it's enough that they are twice differential. It was obtained, there was a result of Alexei Kravchenko, which he obtained sometimes maybe before 2008, but it was published in the paper Differentiability of Fractal Curves, that if we have plane curve, which is 2 times continuously differentiable, and there is a contractive linear map which sends the curve to itself, then gamma is a parabolic arc. And except this parabolic arc and segments, there are no twice continuously differentiable self-affine curves in the plane. Therefore, gamma is a segment of a parabola. And if gamma is not a segment of a parabola, then affine shifts are separated from identity, and we can consider the points, take the endpoints of gamma and take images of all the affine shift, and they will form a discrete system of points on gamma. And then we can show that each of the intervals in this system of gamma can be sent to the other interval, and the images of this interval will never intersect. So we'll get that gamma is the attractor of a multizipper. So we have the following result. For if we have a locally self-affine Jordan arc which doesn't satisfy weak separation condition, then it is a segment of a parabola. And if the attractor of a fine system of affine contraction is not a segment of a parabola or straight line, then there is a finite affine multizipper such that gamma is the attractor of this multizipper. So this is the main result. So I put ahead one more very interesting theorem, but we have not sufficient time to consider it, and maybe we'll return to it sometimes later. Therefore, thank you for your attention.
Thank you for the interesting lecture. So, does anybody have some questions or comments?
Yes, yes. Yes, please.
So if this is not the case, then let us thank our lecturer. And I think we will continue this mini course in 2 weeks exactly, right?
Yes, exactly in 2 weeks. And will we consider the fantastic counterexamples, which were, some of them were waiting 30 years to appear. Some counterexamples in self-similar sets.
Yes, this is inspiring.
Yes.
So thank you once again, and see you all in 2 weeks.
Yes. And even earlier. Yes.
Yes.
Okay, bye.